Hi, I'm Zoë Brand and I'm a PhD student at the University of Liverpool, and this is my poster on subsampling methods for fast backscattered electron diffraction analysis. So EBSD works a lot like SEM, except when we tilt our sample and apply a detector, we can acquire an EBSD pattern. So when we raster scan our sample, we acquire an EBSD pattern at every focal location, which can then be indexed. EBSD is a really useful technique for gaining crystallographic information because of these EBSD patterns. However, it's limited by the speed of our detectors. So the fastest detector can go about 6,700 patterns per second, but really commercial detectors tend to be more at 200 patterns per second. Because of this, we can look at different methods of subsampling in order to speed up our acquisition. So here I've got an example of probe subsampling. So when we look at our mechanism, we have our sample, we acquire a four-dimensional data set, we index our EBSD patterns, and we produce a series of map layers. When we look at probe subsampling, we change how we work with that. So we take our sample, we get a subsampled set of EBSD data, and we produce our subsampled map layer, and we can then inpaint the map layer using BPFA. There's a different way that we can do it called pre-indexing reconstruction, where we inpaint the EBSD patterns, but really we're looking at that as future work. So down here is our BPFA model. If you'd like to know more about that, please talk to Jack Wells. Looking at simulating post-indexing reconstruction, I've used two different map layers, so they're quite different. Our band contrast map is a measure of EBSD pattern quality, so how bright our bands are against the noisy background. And then we have an inverse pole figure map, which is essentially a relative crystal orientation, and it's how we work out the microtexture of our sample. When running through BPFA, I've used a series of subsampling ratios, so from 1 to 25%, and you can see we get really good results from 5 to 25%, and at 1% it really drops off. We can look at a couple of the examples, so we've got the two 5% map layers, and we're starting to get a lot of the useful information here, such as the grain boundaries, but we've got quite a lot of noise going on. There is work we could do to optimize these parameters. However, at 25%, you can see we've got a really good reconstruction, so they're very similar to our fully sampled data set, and essentially give us everything that we need.